Welcome to another exciting digital design class. We've got a homework 7 which is due tonight. And there's also a midterm which has been made available to you, and you were able to open it and look at it, and that is due on the 29th, which is Monday. And what I thought I would do, we kind of, beat homework 7 to death, but I thought I would open the floor to questions about any homework 7 issues that you might still have. Are there any questions? Well, sure. Let's have a look. Number 8 is... Alright. So the question is, this is pretty straightforward, I guess. Let me see if I can shoot. What did I just do? I tried to go full screen so I could see my my own handwriting, but apparently that was not meant to be. Let's see if I can do this. Okay. Just a little difficult to see. So anyways, right, so we have this number, negative 13, and we want to know what is the 2's complement representation for minus 13. So let's start with the positive number, which is so that's the 1's, that's the 4's, and that's the 8's. And so 8 plus 4 is 12, plus 1 is 13. So that is equal to positive 13. And then we're going to need space for a sign bit, so we'll put that in there. And then we'll complement to form the 1's complement, and that'll be and then what we'll do is we'll add 1, because we have to complement an increment to get 2's addition. And well, I believe it. That was an obvious answer, but let me ask if anybody got confused by that. You should all know how to do that sort of thing now. I mean, that's, binary, add the leading 0 so you can have room for your sign, complement, and then increment, and that's your negative 13. And if you like, you can, come up with interesting numbers. Like you could say, well, what is 511 minus 13, right? And what you can do is you can take 511, which is because that's 2 to the 8 minus 1. I think that's 511. Let's see. So that's 1, 2, 4, 8, 16, 32, 64. So that would be 2 to the 8, which is 256. Oh, wait, we need more. Just a minute. There. So that should be 511. Base 2. And now we want to add the minus 13. You know what? I think I should have left myself a space. But if we did it like this, you know what this has done is it's overflowed. I should have left a space in there. That's alright. Don't worry about it. Let's see. So this is 0, we'll call this 2, 4, 6, 8, 16, 32, 64, 128. So what does that come to? Look at a calculator. 128 plus 8 is 136 plus 2. Yep, 138. That sounds wrong. That's all kinds of wrong. This didn't come out right. I have to add an extra 0 to redo it. Forget that example. Pay no attention. I'm using the blinky, the flashy thing. Make you forget all that. Bad example. So anyway, I got the correct answer over in here from the test. So that's for the homework, so that should be all right. Other questions for homework 7? That was question 8. No more homework 7 questions? Done with homework 7? Shall we do some midterm problems? Oh, absolutely. Absolutely. Let's do question 25. What is the 12-bit representation of the 2's complement of the decimal number 2000? But they want a negative. So we have to convert from 2000 to binary. That's our first job. So we use repeated division. Does that look about right? So I got 1, 2, 3, 4, 5. Put in a leading 0. 0, 1. 1, 2, 3, 4. And I need 12 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, works out great. So now we do the complement. Then we do the increment. And that should be equal to minus 2000, base 10. So what I have here is 1 with 1, 2, 3, 4, 5 zeros. And that's correct. 2 ones, yep, and 4 zeros. That worked out great. That's a correct answer. So that was question number 25. Any other questions for homework number 7? No questions? Really? We're done? Then I shall call homework 7 completed, and you guys can submit it. Hopefully we've covered it in sufficient detail so that everybody can get a good score. Let's get a fresh sheet of paper. And then I think maybe it's time to start thinking about the midterm. And what we'll do is take a look at it, and yes. Oops, I just closed it out. You want to go back to homework 7? Oh, to the thing I just did? Yeah. Is that... Okay, sure thing. Sure thing. So what I'm going to do now is I'm going to talk a little bit about this course. This course is divided into 2 sections. The part that includes the midterm all the way up to and including the midterm is what you call combinational logic. And we deal with combinational logic by making the broad claim that we can do everything at 3 gate delays. So however long it is to do a computation like an or an and or an inversion. Times 3, worst case. And so that's a that's something you could do in nanoseconds probably, even with garden variety dog breath logic in the stock room. All that stuff can work really quick. So after the first half of the course, which we will call combinational, we'll move to the second half of the course, which is known as sequential. And there we'll learn how to do counters, finite state machines, and a little bit of computer architecture. Not much, some. So things like memory, stuff like that. We'll look at that a little bit more deeply. So that's what's coming. That's what comes after the midterm. And for now, what we'll do is a comprehensive midterm which will review everything we've done since the beginning of the semester. So might as well start at the beginning because that's a very good place to start. Question 1 is about converting base 8 to base 10. So you all should know how to do that at this point. If there's anything, I'll kind of cover these topics in a broad sort of way, and if you need a review, give me a shout out and I'll just stop and I'll do a few examples. There's a question on base 2 to base 8. So as you can see, it's thematic. We're doing base conversion. There's a question about 2's complement, which of course you know pretty good by now. There's a question about the Boolean laws, and there's a few of those, a few questions like that. Let's see if there's anything else in here. Simplification. Let's see what else. Oh, canonical sum of products, canonical product of sums. Let's see what else we got here. Oh, K-maps, of course. Let's see. So I see 3 variable, 4 variable, don't cares, let's see what else we got. Oh, multiplexers, demultiplexers. You can kind of see there's sort of a lot in this course, right? Because it all sort of builds up on itself. Let's see, there's a little thing in there about vacuum tubes. LEDs. Rectifiers. Adders. Multiplication. It's nothing you haven't seen before. In fact, you've probably seen it all already, at least once. Building large multiplexers. How many you need, that sort of thing, given a certain size. How many packages will you need? What else? What else? More Boolean algebraic laws. More laws, more laws. I'm just scrolling through now. Oh, number systems. So that would be 2's complement, 1's complement, and sine and magnitude. And that's it. That's the whole thing. And it's 69 questions. So not terrible. That's where we are. That's what we've got. Open book, open notes. You can open the test, you can print it out, do it offline, come back in, enter in the answer key. Basically, it's a comprehensive midterm that covers all the big topics that we've seen here in this semester. Any questions about the topics? You guys want to take a minute and take a look at that midterm and see if you got any questions about the midterm? It should be available to you, but if it isn't, tell me. Can you guys see the midterm? That cool? Can you see it? Can you see the midterm on Blackboard? Okay, thank you. That's what I wanted to know. Somebody had to tell me, so I figured I'd call on someone. So yeah, that's the story. We've got the whole midterm in front of us now, and everybody can see it. So if you want to pick out a question that I should try and work for you, I'd be very happy to do that. We can take the next few minutes in class and go over it, or I can cover new material. Shall we do new material? Sounds like nobody has any questions. it's an obvious midterm. Obviously, I've made 29. 29. Well, sure. 29 is directly out of the book. If you like using the book, it's open book, open notes. So sometimes people don't like to read the book, but sometimes it's very helpful. So here it is. That's what you're looking for. That's the little part that goes in the box with the question mark. So the schematic is almost directly out of the book. The only difference is here we're using 2-to-1 multiplexers to choose between B and B prime, but in fact, if you look at the exclusive OR operation, that does the similar thing, and I can show that to you if you like. So that's on page 250. So just to not to put too fine a point on it, if you have let's see, I guess the term is M and B sub I, if it's 0, then the output is going, if M is 0, then the output will just be B sub I. If it's a 1, then the 0 becomes a 1, and the 1 becomes a 0, and this becomes B sub I prime. So by virtue of using an exclusive OR, with B sub I and M going in, we can get B sub I prime coming out. If M equals 1. So this allows you to choose whether or not you're going to invert B sub I. That's why they do it that way in the test. Other than that, it's the same as the figure in the book. I forgot the figure number already. Figure 5.8. Does that answer your question? Sure, sure. Any other questions about the midterm? Yeah, so what is the output of an 8 by 8 multiplier if the input is 1101 0010 times 100 111 00. So here's the rules. 0 times 0 equals 0. 0 times 1 is equal to 0. 1 times 0 equals 0. 1 times 1 is equal to 1. So we know something about these things. Right? That's the identity. This is the 0 part where everything multiplied by 0 goes to 0. That should all be quite familiar to you. The only tricky bit is to keep track of the rows. Right, so 0 times everything 0. Here's another one. 0 times everything 0. So you see I'm shifting the rows as I go. And then when there's a 1 in here, you just copy that number over. And do it again. again, because there's 3 of them. And this is in the way. And then put in a 0. And then another 0. And then a 1. And then you add it up. One plus 1 plus 1 is 1, carry the 1. 1 carry the 1. 1 carry the 1. 1 carry the 1. And you can put a leading 0 in there if you like. And you have 1, 2, 3, 4, 12 ones in a row. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yep, that's correct. That is a correct answer. What do you think of that? It's a lot of scribble in here that shouldn't be here. If I would, and neatness counts. So use graph paper. It helps you. Believe it or not, this is one of those things where it's easy to get the alignments incorrect because all those ones and the zeros start to blur. Any other questions? Number 7. No, I can't find number 7. Oh, there it is. Simplification. Let's do number 7. Simplification of the Boolean expression yields which of the following results? Well, now, how do I simplify this? What does that look like to you? Yes. Yes. So that's A times B. Well, let's just write it out. AB plus A times B prime or C prime, which is equal to AB or AB prime or AC prime, which is equal to A times B or B prime or C prime. What is B or B prime equal to? That is 1. So now I have A times 1 or C. What is 1 or C equal to? 1. So that goes to 1, and now it's equal to A, which is the correct answer. Does everybody kind of see what I did there? B or B prime, you know, if B is equal to 1 and B prime is equal to 0, it's 1 or 0. Similarly, it could be 0 or 1, but either way, B or B prime is always 1. And 1 or anything is going to be 1. So that's how you do that. Any other questions about the midterm? You can use it. Sure. Let's treat ourselves to a fresh sheet of paper. And let's do number 8. The truth table shown may oh geez, I'm leaving out an article. It should say may be expressed by which of the following canonical representations. So what do we got? Two zeros, 1, 0 and a 1, 0 and a 1, and then a 0. That's right. So now this is row 0, 1, 2, 3, 6, and 7. And so now this would correspond to M2, M4, and M6. So F must be equal to sigma M of 2, 4, 6. What do you think of that? In other words, we've summarized which row number has a non-zero element. And this summarizes the truth table. Does that sort of answer your question? Sure thing, sure thing. Any other questions? Midterm, simple midterm, easy midterm, simple professor, easy course. Wasn't that an easy course? Simple course? Simple questions. Number 24. Yep. Let's do that. 24. What's the question? A 3 to 8 line decoder is connected as shown. Okay. I get it. Let's see now. What does it do? That's the question. What does it do? So, let's see if we can make a truth table. So, where will f be equal to 1? Yep. So let's number this. That's radix 10. Sloppily written. There. Now, F, I get my choices. Is F going to be true if all three inputs are 0? Here's all three inputs are 0, so that's not true. Is F going to be true if no input is logical 0? No, because that input is logical 0, so that's not true. So I've eliminated 2. Now it says, well, if 2 out of 3 inputs are logical 0, will F be true? So here, that's not so, because here I see 2 1s and only 1 0, so that's not true. Then it says 1 out of 3 inputs are logical 0. So that's here, 1 out of 3, and here, 1 out of 3, and here, 1 out of 3. So based on the truth table, I get an assertion of F equals 1 if 1 out of the 3 inputs are logical 0. What do you think of that? Does that sound sort of reasonable? Any other questions about the midterm? $25. Sure. You know what? I think it's time for a fresh sheet of paper. How's that? So, what we've got here is a vacuum tube with a grid, and the grid uses a small voltage to modulate a large voltage. And the voltage is going from, this is the heater, goes from the cathode to the anode, also known as the plate. And it says in a triode, this is a triode because it has 3 elements, plate, grid, and cathode. If it didn't have a grid, it would be a diode, which means only 2 elements. And then it would serve as a rectifier or a thermionic diode, also known as a Fleming valve. It says here, one of the answers is the triode can only be used as a switch. Another answer says nobody uses triodes anymore. And then it says triodes cannot do high power. And then it says none of the above. And then it says triodes can be used either as a switch or as an amplifier. And that is true. So you could use this as a switch or an amplifier. And the reason why is because you can have a small voltage coming in that essentially modulates a large voltage. And when you look at the schematics for these things, the voltages indeed are large. You know, the filament could be 6.3 volts, but the plate and anode bias could be 500-600 volts. Serious voltage, not the kind of voltage like you're used to in the lab, like 5 volts. Tubes, vacuum tubes, can have very dangerous voltages on them. So either a switch or an amplifier. Some people, you know, make the mistake of saying, well, if I have a bipolar junction transistor, it's just a switch where current comes into the base to allow current to pass from the collector to the emitter. But that's not true. Transistors are actually amplifiers as well as switches. Depends how you use them, and also depends on their specs. So if you drive these things into saturation, they'll work like switches. But if you drive them in a linear mode, they will work like amplifiers. And that's what happens when you have too much fan out in your TTL. If your TTL is designed to drive only 10 inputs, and you try and drive more than 10, like a little bus with lots of tapping on the bus, then that's going to essentially cause the transistors in the gate to act in funny, nonlinear ways. They will not do what's expected because you put too much parasitic capacitance on the output. They don't drive infinite load from these AND gates, so you've got to limit yourself to the same family of gates and or 10 inputs typically. And even 10, sometimes it depends on how long the wires are, because you get so much parasitic capacitance per foot when you have longer cables. Any other questions about the midterm? Yes. Well, now let's see. Multi-answer. Yeah. Sometimes it lets you input a multi-answer question, but in this particular case, for what kind of voltage drop can you expect from a semiconductor diode? And you know, the semiconductor diodes, those are the ones that use like silicon. They have a well-known band gap. And in fact, if you look at, as it says, page 669, you can actually see the answer. Bear with me a minute. You can see it says, page 669, approximately 7/10 of a volt, small voltage drop. Actually, that's not so small. It's kind of a big voltage drop. I mean, suppose you were running 10 amps, right? So then this diode is going to have to, deal with Ohm's law, right? Voltage drop E equals IR. So, or P equals IE, that's even worse. So the power with 10 amps and the voltage drop is 7/10 of a volt, and now you've got 7 watts or something that you have to dissipate inside the diode, which could burn it out if you don't have a way to heat the sink. Sink the heat. Heat the sink? Yeah, heat the sink. Sink the heat. So I just had this discussion with a student. It's funniest story. I'll tell you the story. One of my students who's taken this course, took the course, decided he wanted to drive a little microcomputer with a peripheral called a transceiver. And the transceiver ran on 3.3 volts. And so what he did to drive it was he put in a little diode. That sounds like a good idea, right? Because it gives you a little voltage drop. He got a special diode, cheaper than a voltage regulator, that drops from 5 volts to 3.3 volts because it drops by 1.7 volts. And I said, well, that's great. You've saved a bunch of money. But can it handle the power? And he said, I don't know. I said, well, wait a minute. You have to know that. Because if this thing is going to be driven by that diode, and this thing is going to take like 100 milliamps, and this is going to have to sink 100 milliamps times 1.7 volts, then power is equal to current times voltage, and you're going to drop by 1.7 volts, and you're going to do 100 milliamps, and so now all of a sudden it looks like you're going to have 170 milliwatts dissipated by this diode as long as this thing is on, and it could be on for a week. So what happens to the diode? It's going to get hot and eventually burn out. And I'm like, you have to think about that stuff if you're going to just start throwing these parts in there. You can't just do that, you know, to a poor little diode. It's not meant for that. It's meant for detecting radio frequencies or something like this. It's meant to output micro watts, you know, 55 microwatts into a detector section for a little radio, not, you know, drive 170 milliwatts continuously. So you just burn it out and your whole thing will be broken. It was a good idea. It was a great idea, but he had the wrong diode. He needed to spec it for the right power. And all he had to do was use the power law. And we just went through that this weekend. And we said, we just got like new printed circuit boards from China. And I said, wait, what's going on here? There's diodes here. And he told me what he had done. And I said, dude, you got to think about this stuff. So there it is. Case study. Case in point. So that actually just happened yesterday, come to think of it. Any other questions about the midterm? Number 13. Number 13. Which of the following expressions is the only correct canonical representation of the function xyz equals y? Well, one thing we know, it's a function. xyz has 3 variables, and it's equal to y. So if I had, I don't know, truth table, that'd be good. I like truth tables. xyz, 0, 0, 1. Got that right. And then f of x, y, z equals y means that's a 1, that's a 1, that's a 1, and that's a 1. And all the rest are 0. Did you see what I just did there? I just copied y to f, because f of x, y, z equals y. Is that sort of sensible? So then I numbered the and now I see where the 1s are, so that f of x, y, z in canonical sum of products form must be 2, 3, 6, 7. What do you think of that? So that's how you do that. Is that sort of sensible? Okay. Yeah, this is number 13. This is number 13. Is that what, that's what you asked for, right? And the answer is 2, 3, 6, 7. Right, because it says f of x, y, z equals y. So I wrote out the truth table for x, y, and z. And then I wrote out what y is, because y is over here, and then I copied it. And then I numbered the rows, and then I wrote the numbers that have the 1s on them over here in the index part of the canonical sum of products. Am I making any sense? Who got confused by this? Be honest. Alright, it sounds like people understand this. Is there another question you'd like me to do? Sure, sure. Let's see, 8-to-1 multiplexers. What the heck, let's get a fresh piece of paper. Alright, so what do we got? An 8-to-1 multiplexer is connected as shown, where the output, f of x, y, z, and z is the least significant input. Which of the following functions does y generate? Which of the following functions? What are my choices? Oh, I see. All right, well, now let's see. I think the first thing you want to do is draw a diagram. And it looks to me like there's an output f of x, y, z with selectors x, y, z, and inputs I'm going to ignore the enable because it's an inverted enable and there's a 0 going in, so that means it's enabled. What do I do here? What's my first step? It's not good if I just answer all the questions. We need class participation. Alex, what do you think? Are you with me, Alex? All right, how about Alexa? Oh, I'm sorry, I should have written the number. That is number 23. How about Andrew? What should I do, Andrew? Can you give me some guidance here? Yep, What's my what's my first step? Guide me through the problem. That sounds like a good idea. I like that. So let's do a truth table. Now what should I do? I'll number the truth table just because I'm a nice guy. So, what do I do, Andrew? Yeah, you don't really have to, right? Because we know that we have 8 inputs and we've got a separate constant for each one. So we should be able to obtain the function f by inspection. You think you could do that? There you go. Well, what about row 1, row 3, row 5, row 6, and row 7? That's a 0. So that's what I got so far. Now let's compare what we have here. What is f equal to? Anybody have any insight into this function? Yeah, f equals z. And that's that. It's a wire. You could replace this whole thing with a wire. Right? Just take z and wire it to f. Bang, you're done. Don't even need the 8-to-1 multiplexer. Because you can replace, that can't get simpler than a wire. I mean, that's cheap, easy to build, nice and small. It's a wire. Did anybody get confused by this? It sounded like we had a little trouble here. I wasn't expecting people having trouble. This was not a trick question. This is a straightforward problem with the multiplexer and its inputs. Make a truth table, observe how it works. This is a very simple sort of problem. Want to ask any more questions? More questions? 29. We just did 29. 29, they want to know, didn't we just do 29? They want to know what goes in the, yeah, we did it. That's all right. You know, if you wanted to, you could look on page 250. Here we go. Sure. So yeah, page 250, figure 5 point, whatever that says, 5.8. So what was the other question? Number 30 something? Sorry. Oops. Okay, number 30. We'll do that. I thought I was having a senior moment. So can we do 29? Wait a minute. Didn't we just do that? Yeah, let's do number 30. Which of the following binary multiplications is correct? So let's see now. Two 4-bit numbers are being multiplied together. So let's see. Could try a few of them, but let's try this. 1101 times 1011 times. So that's 1 times all of that is 1011 1011 000 1011. That's 128 plus, looks like 15. Looks like 133. What's this number? That's 12, that's 13. That's 8, 2 is 10, plus 1 is 11. Did I screw this up somehow? Carry the 1. Oh, yeah, that is 143. Forgot to carry the 1 over here. So, yeah, that works. Multiplication works. Yay! When you do it right and remember to carry your thingies. So that's the... Did anybody get confused about multiplication in binary? I did it over here in decimal just so you could see that it works. Only to find out that I don't actually know how to multiply. But I figured it out eventually. And any other questions? Number 32. Compute 7 minus 1 using 2's complement. Assume there are only 4 bits available to represent the numbers. So 7 minus 1. 7 minus 1 is 6, right? I could probably negate that and get and that should be an answer, but maybe not. Let's see. 7, 0, 1, 1, 1, and then minus 1 using 4 bits is going to be 0, 0, 0, 1 with 4 bits plus 1. So that's going to be 1, 1, 1, 0 plus 1, which is 1, 1, 1, 1. And that's what you get. And that is 6. I don't know why I thought I would negate the 6, but in fact, it's positive 6. So that's correct. 7 minus 1 is 6. Every day of the week. Good deal. Anybody got any questions about what I did? Nope. No questions? How about another question for the midterm? Question 34. Let's see. A certain black box has 4 inputs and 16 outputs. Only one of the 16 outputs is asserted for each unique combination of inputs. What could that black box be? So, let's think about this. A multiplexer that's a 16 to 1 could have 4 inputs for selectors and 0 through 15 inputs, and that would be a mux, a multiplexer. But he says here it only has 4 inputs and 16 outputs. So what could have 4 inputs? 16 outputs. What could that be? And then 16 outputs. And only one of the outputs is asserted for each unique combination of the inputs. What do we call this black box? Let's see. I'm going to call on somebody. How about Joseph Crowley? I never call on you. What is this called? That's correct. Thank you. So That's the answer to question 34. Any other questions about the midterm? Let's do question 33. Oh no, the pointy-haired manager got a deal on multiplexers. And they are all 4-to-1 multiplexers. That's all I got is 4-to-1 multiplexers. But I got a lot of them. And they were really cheap. 4-to-1, 2, 3, 4. To select your inputs. 0, 1, 2, 3. And that's a mux. And I have a lot. Infinite multiplexers. Infinite. Lots and lots. What can I do with lots and lots? How many do I need to build a 32-to-1? I need a 32-to-1 multiplexer. So that's 0 through 31. And 8, 16, 32. Yeah, so it's going to be A, B, C, D, E. And then function output. This is a big honkin' system here. 4-to-1 multiplexers. How do I handle this problem? How many do I need in the first stage? Got to have 32 inputs. Zero through 31. So that's going to need, I don't know, maybe 8 4-to-1 multiplexers, because that'll give us 32 inputs. And then the next stage, right, because this is 8, it's going to have 8 outputs. 0 through 7. So the next stage, you've got to have at least 2, right, because it's the only way to handle the 8 inputs. So that'll give you 2. And the next stage, you're going to need 1. You only use half the multiplexer. And so, looks like I need 11. Right? 8 plus 2 plus 1. Because 8 will give me 8 times 4, or 32 inputs, but it'll give me 8 outputs. And then 2 will give me 8 inputs, only 2 outputs. And then 1 will give me 4 inputs, but only use 2 of the 4 inputs. And I'll get 1 output. So I need 11. Did everybody kind of understand that one? Who got confused? Nobody? All right. Next question, please. No questions? Number 38. Number 38. The following truth table is for a 3-input AND gate. Find the output given inputs A, B, and C. Well, first of all, how do you make a 3-input AND gate? The answer is get an AND gate, then get another AND gate. Now, do the truth table. Right over in here, you're going to have A and B. Right over in here, you're going to have A and B and C. So how do you fill in the truth table? When will F be true? F equals A and B and C. When will F be true? Let's find somebody. Bridget, when will F be true? Well, A has to be true, B has to be true, and C has to be true. So it'll be 1 times 1 times 1. And that will equal 1. If C is 0, 0 times anything is 0, so the only time when F is going to be true is on row 7. And all the other times it's going to be 0. What do you think of that? Am I making any sense? I don't know if the ordering is correct, but yeah, on my screen it looks like option C. Yeah, yeah. So you know, if you think about it, AND gates are true when both inputs are true. Take another AND gate. Now it's true when all 3 inputs are true. Take another AND gate, and now it's true when all 4 inputs are true. But only if and only if all 4 inputs are true. If any one of the inputs is not true, then F will not be asserted as a 1. It will not be true. So you can chain this as long as you like. But typically you would just buy an 8-input AND gate if you needed to be dealing with 8 inputs. You wouldn't chain it like this because it just delays things a bit. Any other questions? I think we might have time for one more question. It's 2 minutes, a little less than 2 minutes. Well, I tell you what. Why don't you guys take a look at this midterm and bring your questions with you to class on Thursday, and I will be very happy to entertain your questions. It's cold out, but it's clear. Enjoy the rest of the day. I think no sense starting another question we can't finish in the next minute and 20 seconds. And stay safe. Thank you for your attentions. Thank you. Thank you.